Hey guys! Today I'm going to be talking about the alternating series test. But before we dive down into this topic, I'm just going to talk about what an alternating series is and what types of alternating series does this test work for. So it looks something like this, all the way to infinity, and n is equal to some sort of number. So it could be 1, it could be, say, 0, it could be, say, 2, right? And then we have -1 to some sort of exponent of n. It doesn't have to be n, it could be n plus 1, it could be n minus 1, something like that. So this -1 with the exponent helps make the series alternate. And then we have some sort of expression here, bn. So an example of a series that looks something like this, that alternates, looks something like this. So with this series, it alternates because if we were to plug in n equals 1, we would get the following. We would get this whole thing to become, I'm going to plug in n equals 1 into each of these n's, and then this is going to be to the exponent of 0. It's going to be 3. It's going to be 2 minus 1. We get 1 here, we get 3 here, and we get 1 here. Finally, we get 3. So this is for n equals 1. We plug in n equals 1 in here. Now let's try n equals 2 and see what happens. So if we were to plug in n equals 2, then we would get, just plug in n equals 2 into each of these n's. And we would get -1 here to the exponent of 1. 3 times 2 is 6. And then 2 times 2 squared, 2 squared is 4. 4 times 2 is 8. We subtract 1 here. Get -1 here. And then 6 over 7. And this would be, at last, -6 over 7. Now, if we were to plug in n equals 3, we would get the following. We would get -1 here, and then plug in 3 to this n, minus 1, and then 3 times 3. So we put in 3 right here. And then 2 times 3 squared minus 1. And this would be -1 squared, because 3 minus 1 here. And then this would be 9. And then 3 squared is 9 here, and then 9 times 2 is going to be 18. Then we subtract 1 right here. And then we get -1 squared, which is just going to be +1 times 9 over 18 minus 1 is 17. And then here we will get 9 over 17. And as you can see here, this number is positive, this number is negative, this number is positive. So we kind of alternate. So if we were to put this series together, we have 3 first. Then we will have -6 over 7 that comes next. And then we have 9 over 17 that comes next. And notice that I'm not writing it in commas like this, because this is a series, so we have to add these numbers together. So we would have to look at it this way. And it keeps going on and on and on. So it's going to alternate between positive, negative, positive, and negative. That's how the pattern works. Positive, negative, positive, negative, positive, negative. So it keeps going, and so that's why it's an alternating series. So now let's dive down into what the alternating series test is. Okay, so now we're going to talk about the alternating series test and what it is. So say we have a given series that looks something like the one we see before. it doesn't have to look like this. So like the basic form is basically something like this. Doesn't have to be n minus 1, it could be n, just like before I mentioned, or n plus 1. This doesn't have to be n equals 1, it could be like n equals 2, something like that. So let's say we have this given series and we find that first bn plus 1 is less than or equal to bn. And so it's like it's decreasing basically this this part. Basically the bn is decreasing eventually. Then that satisfies the first condition. This is the first condition, and then we have the second condition, which is basically the limit n approaches infinity for bn, so just this part, so without this negative part, okay? Even for this part, it's without the negative part. And if this is equal to 0, then that satisfies the second condition. So if we satisfy both of these conditions, what can we conclude? Well, based on the alternating series test, it basically says that we can conclude that the given series is convergent. With this test, we typically use it for alternating series, so you will usually see like -1 to some sort of exponent. So that's why I explained in depth how an alternating series kind of works, so you kind of get an idea that it alternates between a positive, negative number when the terms are being added. So let's say if we took this given series, for example, and we proved number 1 to be true and number 2 to be true. Well, we actually haven't done these proofs yet, but let's say we actually did that, then the given series is convergent. Okay, so now we have to determine if this series converges. So we're going to have to apply the alternating series test. Well, the alternating series test, if let's say one of the conditions fail, then basically what will happen is we can't use that test and we will have to use a different test to find if it's convergent or divergent. So we're trying to see if this is convergent. So we're going to use a test and see if it meets the condition. So the first condition is we have to find out if this is true. And is it true? Well, here's a great strategy you can use. So we know our bn is equal to 3n over 2n squared minus 1. And we could change this to f of x is equal to 3x over 2x squared minus 1. Now let's differentiate this f of x, and so we can get the derivative, and then we can see if it's decreasing, because if the derivative is negative, then that means it is a decreasing function. So we are going to use the quotient rule to differentiate this function. So we're going to find the derivative of the top, which is just going to be 3, because derivative of 3x is 3. And then we have to multiply by the bottom, which is 2x squared minus 1. Then we have to subtract the derivative of the bottom, which is just going to be 4x. And then we have to multiply by 3x, which is just the top. And then we have to square the bottom as according to the quotient rule. Now we are going to use the distributive property, so 3 times 2x squared, 6x squared, 3 times -1 is going to be -3. Now 4x times 3x is going to be 12x squared, and add in the negative, so -12x squared, and then all over 2x squared minus 1 squared. And then we have to see these like terms, 6x squared minus 12x squared, that's going to give us -6x squared minus 3, and this is going to be all over 2x squared minus 1 all squared, just like that. Okay, so now that we have differentiated our function, we are going to look at the numerator and the denominator. So with this denominator, we can see it's evidently greater than 0, and that is because we are squaring this whole thing, so it's obviously going to be a positive number. On the other hand, this numerator will for sure be negative because we have subtraction signs here, and the squared number is just going to keep getting more negative and more negative. So we're adding kind of more negatives as this x increases. So we are going to say that this is less than 0. And since this numerator is less than 0 and the denominator is greater than 0, we have a negative and a positive. A negative divided by a positive will give us a negative, so that would mean that this f prime of x, the entire thing, this whole thing is negative. So we can say that this whole thing is less than 0. And since the whole thing is less than 0, therefore f of x is decreasing. And if f of x is decreasing, then that basically means the next term, because remember we defined earlier bn here, right? And then we change it to f of x, so n is kind of like the same as x. So we can conclude that bn plus 1, like the next term, is going to be less than the previous term because it's going down. It's going down, it's decreasing. So this is our first condition. And since we have proved that bn plus 1 is less than bn, right? We proved this to be true, then therefore we have satisfied our first condition. Now it's time to move on to the second condition and see if that is true as well. So we checked our first condition. Now we're going to have to check that our second condition applies as well. So our second condition is we have to check the limit. So for bn, so this part, so we have to see if it's equal to 0. Is this true? Well, let's find out. So we're going to see that. And we see, okay, so if we were to evaluate the limit, we see that as n goes to infinity, this 3n is going to go to infinity, the numerator is going to go to infinity. So is the denominator, because we're squaring here, it's just going to get bigger. So we have to use something called L'Hopital's rule. So we're going to differentiate the top and the bottom. So let's do that. So this is going to be 4n, and then if we plug in n goes to infinity at the denominator, because we only have n in the denominator now, it's just going to keep getting bigger. It's going to get really, really big. It's going to go to infinity. It's going to be a really, really big denominator. And this is in comparison to the really, really, really tiny little 3. So the really tiny little 3, really big denominator. And that's just going to make this whole thing go to 0. Because we're dividing by really big numbers. We're making the number extremely, extremely small. This entire number. So we proved that this is equal to 0, and we satisfied the second condition as well. So since we satisfied both conditions, then we can conclude that therefore the series, this given series, converges. Okay, so now for our second question. And in this second question, we can see that we have to apply trigonometry. So this is kind of like an application type question. So let's look at the numerator. We can notice something about it. And that is, we can rewrite it. So let's say if n equals 1, what's the numerator going to become? Plug in n equals 1 into this n, and we are going to get cos of 2 plus 1 is 3, so 3 pi. And cos of 3 pi, what is cos of 3 pi? So if we were to draw this, all these 4 quadrants, we're going to look at it and say, okay, this is 1 pi, 2 pi, 3 pi. Okay, so we end up here, and that's going to be negative 1, 0. And since it's negative 1, 0, okay, well, this is 1 here, our radius is going to be 1, and This is our x, this is our y. Okay, so x over r, so -1 over 1, that's going to be -1. Now for n equals 2. So n equals 2. Cos, we're going to plug in 2 here. So cos 2 plus 2 times pi. And we are going to get cos 4 pi. And then we look at this diagram again, CAST diagram. And we go, okay, well, it's going to be 1 pi, 2 pi, 3 pi, 4 pi. And we end up here. This is going to be 1, 0, so this is also 1. So 1 over 1, it's going to give us 1. Now let's look at n equals 3. For n equals 3, we are going to get cos. We have to plug in 3 into this n, so we're going to plug that right in here. We are going to get cos 5 pi, and cos 5 pi. Let's look at this diagram again, CAST. So 1 pi, 2 pi, 3 pi, 4 pi, and 5 pi. So right here, so -1, 0. So let's see, this is 1 here, so -1 over 1. So -1 over 1, that's going to give us -1. So that's for n equals 3. Now n equals 4. N equals 4, so cos, so we plug in 4 into this n. Not sure we noticed the pattern yet, but there is a pattern. So cos 4 plus 2 is 6, so 6 pi, just like that. And then we look at this diagram again, so 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, and 6 pi. This is 1, 0. So 1 here, 1 over 1. It's going to give us just 1. So as we can see here, this is -1, this is 1, and then it goes to -1 again, and then it goes to 1 here. So we can see that it alternates. So this exhibits the -1 to the exponent of something in an alternating series. So that means we can rewrite this numerator as something. So we can rewrite it as -1 to some sort of exponent there, and that can be n minus 1, n plus 1, or n, or just n, or something like that. So let's see, if we put in -1 to the exponent of n, let's see what happens. -1 to the exponent of n, let's say n is equal to 1, we would plug that in, and it's going to give us this. It's going to give us -1. It's an odd exponent. And let's say if we plug in 2, we would get 1, and that's going to give us this. If we plug in 3, odd exponents, it's going to give us -1 as found here. So great, so that would work. So we can change this top chunk to -1 to the exponent of n, and we could rewrite the series. So we can basically say that this is equal, rewrite this entire series. So this is going to be equal to this. And we see, hey, this is an alternating series. Now we can just basically, to see if it's convergent or, see if it's convergent, we just have to test it out and apply the two conditions. So we are going to do that, and our first condition we need to see is whether bn plus 1 is less than bn. Okay, well, what do? We look at our bn, and what's our bn in this case? Is 1 over 4 plus n to exponent 3, 2, just like that. Because our series typically has the form of something like this. Something like -1 to exponent of n, and then there's a bn right here. So that's the bn without this exponent. And then our bn plus 1, we just have to add 1 and plug this right into n. So we are going to do that. So it's going to be 1 over 4 plus n plus 1 to the exponent of 3 over 2, just like that. And we can see, okay, let's compare if this is true. Is it true? Well, we know that n plus 1 to the exponent of 3 over 2 is greater than n to the exponent of 3 over 2. And that is because we're adding 1 here, so it's a greater base. So when we have a greater base, it means it's greater, and even when we add 4 to it, to both sides, we are going to get that this is still true. And then if this is greater, then we can basically conclude that this is less than this one. And that is because it's a really, really, really big denominator, right? I mean, I wouldn't exaggerate it, but this is a bigger denominator in comparison to this denominator. So if the denominator is greater, it just means that this whole thing is going to be smaller in comparison, because we're dividing by bigger numbers. So we recognize that this is the same as bn plus 1, and we recognize that this is the same as bn. So we can say that bn plus 1 is less than bn. Just like that, and we have proved our first condition. So in the beginning, we were asking whether this was true, and we found that it sure is. Now for our second condition, and we are going to see as to whether when this goes to infinity, where bn is equal to 0. Is this true? And we are going to find that out. We're going to evaluate this limit, and as mentioned previously, our bn is 1 over 4 plus n to the exponent of 3 over 2. And we can see evidently that when n goes to infinity, this denominator gets really, really big as well. And when this denominator gets really, really big, when we compare it with tiny little one, really big denominator, then that just means that this whole thing is going to go to 0. And since it's going to 0, then that means we have satisfied our second condition, which states that this limit has to be equal to 0. And since we have satisfied our second condition and our first condition, then that basically concludes that our given series, our series that we were working with, this alternating series, is convergent. So we can say it converges. And then we remember that our original question was actually we know this is a cosine, so it was cosine n plus 2 pi. Okay, we have to rewrite the original question so we can answer the original question. And since this converges and they're equal, therefore this series also converges. And this is by the alternating series test. Okay. And this brings me to the end of the video. Thank you for watching. Feel free to let me know down in the comments below what you think about the alternating series test and whether this video has helped. Have a great day! Bye!